All right, hello everyone and welcome back. In the last video, we introduced the centripetal force equation. So I'm going to write that up here. Fc equals mv squared over r. And I remind you that there is no such thing as centripetal force. Like there is an Fw or an Fg or an Fn or an FF or an FA. Those are all real forces, but centripetal force is really just a vocab word. The word centripetal means towards the center. This tells me that there is a force, O, and it's towards the center. So really what this lesson is about is we know there's a force towards the center. We are trying to figure out what that force towards the center is. And we're going to figure that out by drawing a picture and just looking at our free body diagram. Our free body diagram will tell us the force that's acting towards the center. And once we know the force that's going towards the center, we can kind of continue with some mathematical derivations until we kind of hit a dead end. And that dead end has some applications in our real life. And that's what I want to talk about. Okay, so you'll catch on once we get rolling here. All right, so I'm just going to make up some, I'm going to call them classic examples that you run into in a lot of physics problems. All right, so one example is we have this box sitting on the floor. And I'm turning the box into a dot. And this girl attaches a string to the box. And she's sitting on the floor. And then she like spins the box around in a circle. It looks like it's actually going the other way. So she's going like this. I don't know why she's spinning the box around in a circle. But anyways, you and I walk by and we say, oh, look at that. She's spinning the box in a circle. And if you see something going in a circle, you can write down the circular motion equation. And by the way, for those of you who are taking the AP exam, you get points for showing your work and you get points for your derivations. Anytime you have something going in a circle, you need to write this down. You get a point for this. All right, then you get a point for recognizing centripetal force is not a real force. It just means there's something going towards the center of the circle. What is that? And then you look at your picture and you say, oh, well, what's going towards the center is that string. And the force that's in a string is called tension. So I'm going to write down Ft. And so because of that, I'm going to replace the centripetal force with Ft. You'd get a point for this on the AP exam. And I'm going to call this a working relationship, a working equation, a mathematical relationship. So you might find a physics problem that you end up using this working relationship. We'll just leave that there for now. All right, let's look at another one that's a little bit more complicated. So there's a classic physics lab where you take a glass tube. So here's my glass tube. And then you take a stopper. So here's the stopper. And then you take a piece of string and you tie the string onto the stopper, and then you thread the string through the glass tube and it hangs down here. And then your hand goes on the glass tube. So I'll draw a hand. It's a really bad hand. It looks like a foot. All right. So my hand is on the glass tube and I'm supposed to spin the stopper so that it goes around in a circle, maybe over my head. Well, you'd find out that it's impossible. You're not allowed to touch the string, by the way. So you're holding the tube and you're spinning this around and you find out it's impossible, like it keeps flying away. But it is possible if you take a weight and tie it on the bottom here. So I don't know, this could be 0.5 kilograms, let's say. You can tie any weight on here. But once I put a weight down there, it's like, oh, okay, I can spin now. And you end up finding, you have to spin at constant speed again, and you end up finding like this perfect speed to spin the stopper that it works. You can spin that stopper in a circle. So let's write down what we see. So we see a stopper going in a circle. So I'm going to write down FC equals mv squared over r. And then I say, oh, there has to be a force towards the center. I wonder what it could be. And then you look at your picture and you see this string. And you think, well, maybe it's tension. So you write down FT. But then you realize that, oh, wait a second, that it's not tension, because when I didn't have that weight, I didn't have any tension. It really was this weight, the FW that I hung down here, or FG if you use FG. It's really the FW that I hung down there that's providing the tension or making the tension in the string. So that tension is created by the FW. So I'll put FW equals mv squared over r. And FW would be that mass times gravity equals mv squared over r. Ooh, but this is tricky, because look at this. I have an m here and I have an m here. But you cannot cancel m's. Cannot cancel m's. Why? Because this m is the mass of the weight. So I'm going to write the word weight in here. This m from mv squared over r is the mass of what's going in the circle. That's this. That's the mass of the stopper. And so in this particular relationship, when you're spinning something and you have a weight tied onto it, those m's stand for different objects, so I can't cancel the m's. We're going to find out that this is the only example where I cannot cancel the m's. All right, let's look at another fun one. This one is, I'm going to call it a car on a flat road. Or it could be a penny on a turntable. Anything that's sitting flat, but going in a circle. But let's talk about the road for a minute, because it's a really practical example. So maybe here's a freeway, and you've seen clover leaf exit ramps before. It's like a circle. So let's draw the circle of that clover leaf exit right there, or this one right here, okay? So we have this road coming like this. We're going around the circle, and then our goal is to go this way. All right, but let's put our car right in the middle of this. So I'll draw my car here. And we know we're going this way. So I see my car going in a circle. So I'm going to write down the circular motion equation. And there has to be a force going towards the center. There has to be. But unlike these two examples that were a piece of string that I could see, this force is invisible and I don't really see it. But think about it. What if it was a snowy, icy day? You might find it hard to go around that circle. Because you know what force holds you in place when something's going in a circle? It's friction. What about a penny on a turntable? What holds that penny in place? It's friction. So it's invisible, but we know it's friction. So I'm going to replace this with friction. And you might remember that friction is equal to mu times Fn. And you might remember that Fn is equal to Fw. Car pushes on road, road pushes back on car. So mu Fw equals mv squared over r. And now I'm going to replace the Fw with an mg. And let's talk about these m's. This m from friction came from the weight of the car. This m is the mass that's going in a circle, which is the car. So these are both the car. So therefore, I can cancel them. So what's left? Mu g equals v squared over r. All right, that is not an equation. You cannot just pull that out of a hat and plug in numbers and go from there. On your AP exam, you have to start with this and you have to go through and you have to derive this. Now that we have derived this, now we can use this working relationship to apply it to something. So let's pretend for our first example that you are a civil engineer. Civil engineers design roads. So let's talk to ourselves. I'm trying to figure out how big this clover leaf needs to be, at least this part of the clover leaf. So let's say that I'm trying to figure out the radius, like how big it should be. I just have to kind of make up some numbers here and talk to myself. So this radius is going to depend on these factors: the coefficient of friction, gravity, and the velocity of the cars. So you might talk to yourself and say, well, coefficient of friction, like normally coefficient of friction, it's a nice dry sunny day, rubber tires on a concrete road, that could be like 0.8 or something, 0.8 or 0.9. But what about those snowy, icy days? Like this coefficient of friction could drop down to like 0.1. And we're going to build our clover leaf on Earth. So that's going to be a 9.8. And what about the velocity of the cars? Like, how fast do you think the cars are going to try to go around this circle? Like, are they going to try to go around 45 miles an hour? Do you think they're going to go like 60 miles an hour? Oh no, they're coming off the freeway. What if somebody like is going 75 miles an hour? They're supposed to slow down, but what if they don't? And so you have to figure out, like, what velocity are you going to design a safe clover leaf? And you might decide that I'm going to design a safe roadway for everybody. Like, I'm going to put in 100 miles an hour, but I'd have to convert that into meters per second. And so you put in 100 miles an hour, like, I'm going to make sure that those people are safe. And then you calculate R and you find out that this clover leaf has to be humongous. And then someone says to you, you can't do that. We don't have that much space. There's like shopping centers around there. You only get this much space. Oh, I only get that much space? Then you're telling me my R value, coefficient of friction, I might be able to take it down to 0.4, like make it safe on a rainy day, but people are just going to have to know that if it's icy, they're just going to have to slow down. This is going to be 9.8. And maybe this time I'll calculate the velocity and say, we made a clover leaf that's only safe for 35 miles an hour. And so we just put up a speed limit sign as you get off the freeway, 35 miles an hour as you go around this clover leaf. And just know that when you see those things, somebody put that there telling you that this clover leaf was made safe for those speeds. And if you exceed those speeds, then you can go off tangent to the circle and end up in the ditch. And so that's how our mathematical relationships can help us in real life. All right, let's look at another fun example. This one is an amusement park ride. This amusement park ride is sometimes called the rotor. Sometimes it's called the gravitron. But basically, it's a big cylinder that you stand in. So I'm just going to put a person right here. You stand like this. And so there is a floor like this. But as the ride spins and goes faster and faster and faster, the floor drops. And so when the floor drops, the people are just stuck to the walls of the ride. So I'm going to draw somebody who's stuck to the wall of the ride over here that we can use as our example. But I'm going to have a little kid also here. We're going to have a real big person. We'll make him the big person over here. And so we have a bunch of people on the ride. And but let's use this person as our example. So first of all, I see a person going around in a circle. And so I'm going to write down FC equals mv squared over r. So there has to be a force towards the center. I just got to figure out what it is. It's invisible, and this one's a little trickier to find. So I'll help you figure it out. So if I had to draw a free body diagram of this person, he would have his FW going down. And usually FW goes down and then the normal force points up. But the normal force is the force that a surface presses on an object. And so what's acting against this FW here is not the normal force. It's actually friction. Because if the person was sliding down like FW, he would have friction against that wall. And the normal force is the force that a surface presses on the object. And that's what this is. The surface, the wall, pressing on the object. This is the normal force. It's the normal force that's pointing towards the center of the circle. Let's go over here for a minute. Friction equals mu times Fn. So Fn would end up being equal to friction over mu. So I'm going to replace that with friction over mu. And when you look at this friction and you look at this, that person, when they're stuck to the wall, they stay stuck to the wall. That tells me that they stay in the same plane, that FW has to be equal to FF, because if FW was bigger, they would slide down. If friction was bigger, they would go up, but they stay there stuck to the wall. So friction is equal to FW. So I'm going to replace friction with FW, but I'm going to save myself a little bit of writing because FW is equal to mg. So we replaced friction with FW and then replaced the FW with an mg. And Let's talk through the M's again. This is the weight of the person. This M is the M that's going in a circle, which is the person. So cancel, cancel. And so this time we end up with G over mu equals V squared over R. So this relationship could help me design a safe amusement park ride. So let's talk about that. So all of the people are on the same ride, which means they're going at the same velocity. So we would know their velocity. I'm just going to write V. They're all on Earth, so that's going to be 9.8. The radius of the ride is the same for all of the people. So all of these things are the same, except for this, except for the coefficient of friction. What does that mean? It means when I look at the people, some people are up higher than other people. Like, why is this big person up higher than this little person? Seems like the big person ought to have fallen down more. The only thing that's different about these people is the coefficient of friction. What does that mean? The coefficient of friction of a person. The coefficient of friction is the friction that exists between their clothing and the walls of the ride. This big person could be wearing like a sticky leather coat. They're going to be higher up on the ride than somebody who's got a little slinky windbreaker who's slippery. Their mu is going to be smaller and you'll find them lower on the ride. So when the floor drops, people all like slide into their positions, and they're sliding into their positions based on what they're wearing. And so that relationship can help us understand what we see when we look at people on a ride like that. All right, the last one is short and sweet. So this one I call a satellite in orbit. So a satellite in orbit could be a planet going around the sun. It could be a moon going around a planet, or it could be a spaceship like going around the Earth. So however you want to consider it. So let's call it, for this example, a satellite in orbit. Let's call this the moon. So I'm going to call it M for moon. And so this is going to be the Earth. All right, so I see the moon going in a circle. I see something going in a circular path. All right, what holds the moon in place? Like, what is the force that's going towards the center? Again, it's invisible, but it's gravity. And gravity is the gravitational force. Fg equals mv squared over r. And we know the equation for Fg is the universal gravitational constant, m1, m2 over, I'll call it d squared, equals m v squared over r. All right, this r stands for the radius. Like if I turned this into a dot and I turned the Earth into a dot, that'd be the radius. And it's also the distance between them. So these two variables are the same. You can turn them both into d's, or you can turn them both into r's. I'll just right now turn this into an r. All right, so one of these m's stands for the satellite, one of these m's stands for the Earth. This m stands for the satellite. So the mass of the satellite and the mass of the satellite, S and S, would cancel. This becomes the mass of the Earth that stays there. And one of these r's can cancel with the squared. And what I have left is the universal gravitational constant, the mass of the Earth in this example. I have one r down here, and I have v squared over here. So obviously, if I square root that, velocity, the mass, the R, V, I'm going to call this orb. This is the velocity that you need to orbit something. And this is the something that you're orbiting. The mass of the Earth, this is the velocity that I would need to orbit the Earth. And so this is a practical relationship, and we run into this relationship when we look at Kepler's laws. Okay, so it seems like we're doing a lot here, but we are. So it gets a little bit deeper. And you know what? I think I'm going to make this a separate video. So give me a sec.